and welcome back. So in our previous segments, we've been talking about some properties that all waves have. And so here's yet another property that they have a speed. So waves travel at a certain speed. And so notice I'm using the regular V to stand for speed, and this would be in meters per second if we're talking about official metric units. All light travels at the speed of light. Okay, so that means that a radio wave travels at the speed of light, 3 times 10 to the 8th meters per second. So going at that speed, you could get to the moon as quickly as you could blink your eyes. If you want to go to the sun going at light speed, it's going to take you 8 minutes to get there. If you want to go completely across the galaxy, the Milky Way galaxy, going at the speed of light, it's going to take you like 100,000 years traveling at the speed of light. So radio waves travel at the speed of light, infrared travels at the speed of light, visible travels at the speed of light. So all kinds of light, they always travel at the speed of light. So if you're one of my students and you're taking the exam and I say which is faster, visible light or a gamma ray, you would say that they're samey same. Okay, they're the same. They're same speed. Now sound waves, on the other hand, that's different. So sound waves actually travel at different speeds depending on what they're going through. So the speed of sound in air is roughly 400 meters per second. Okay, but the speed of sound going through water or going through steel would be different. So in general, the denser the material that the sound wave is traveling through, the faster it's going to go through. So here is a type of question that I would like you to be able to do. So what is the wavelength of a 91.3? Now what do you think that M stands for? Mega. So it's a 91.3 megahertz radio signal. So the first thing you do is you're going to write down what you're given and what you're looking for. Now the clue is 91.3 megahertz. So the hertz, that's frequency. And then the special letter that we used for frequency was the thing that kind of looks like the bird. And so the frequency is 91.3 megahertz, but we need to change that to regular old hertz. So we're going to multiply that by 10 to the 6th, a million. Okay, and then it says what is the wavelength, and we know that the letter for wavelength is lambda. Okay, our next step is what formula do we know that has a speed and it has a wavelength and it has a frequency? Okay, well we just did that one, and so it says select the formula that connects the letters. And so the speed we're going to use is the speed of light because it is light that's traveling, the radio signal. So we're going to say 3 times 10 to the 8th equals 9.13 times 10 to the 7th. Did you see that I changed it from 91.3 to 9.13, but in order to do that I had to change it from 10 to the 6th to 10 to the 7th. So little details like that can get you messed up when you take the exam. But you're going to solve that for the letter lambda, and lambda turns out to be 3.3 meters. Radio waves have very large wavelengths. And so on our chart here, let's go ahead and put that down, that radio waves have large wavelengths. And then let's put on the opposite side over here that the gammas have the smallest wavelengths. These things can be up to 1 kilometer. The wavelength of a radio wave could be as large as a kilometer. The wavelength of visible light is approximately the size of the atom. And then the wavelength of gammas over here is about the size of the nucleus of the atom. So they're incredibly small. All right, so let's go on here. And okay, there we go. So now we are on the Doppler effect. And so let's talk about that in our next segment.